Hello, and welcome to the third of our systems engineering lectures, where we look at systems engineering and how to build the product right. My name is Tim Kerby, and I'm the CEO of Edinburgh Systems Ltd, a consultancy specialising in systems engineering and product management. Why do we need systems engineering? If you look at this chart, we have two axes for complexity and robustness, and a whole variety of different products and industries in there. What we find is as the complexity and the robustness increases, there's more need to use systems engineering, but it's valuable across all systems of all sizes. Down in the bottom corner, for the most simple products, the systems engineering is useful because systems thinking results in better components. We can think about how they interface and how they can be optimized as part of the system. We can look at composability, so that's how we have standard interfaces that mean you can swap in a better component for another one, and how we can do the product line engineering. So a series of products look similar and behave in similar ways and have different functionalities and different levels of performance. And it helps identify the right problems to solve with these more basic components. As we go up in complexity, systems engineering is needed because the increasing complexity makes it much harder to use traditional engineering techniques of documents, presentations, emails, to be able to manage the delivery of that product and make sure that all your engineers are on the same page. So it ensures we build the product right and avoids the rework there that is caused by human errors. And then as the robustness goes up, systems engineering is mandated. So for safety and security in systems, we have to comply with the industry standards. So in automotive, it's ISO 26262, and industrial IEC 61508, that prove that the system we're building is robust. And it enables the traceability of those requirements to validation to make sure that we've actually built what we say we're going to build. So in the top right-hand corner, where you have things like automotive, IoT, self-driving vehicles, we have both the complexity and the mandated systems engineering, and that's where it's perhaps the most important to apply it correctly. Looking at the differences between systems engineering and traditional engineering, the systems engineering is usually top-down. We break down the system driven by the stakeholder needs. Traditional engineering is often bottom-up and driven by technological challenges and solving the interesting problems. Systems engineering focuses on stakeholders, whereas often traditional engineering is taking a product and looking at how it can then be sold and marketed. We look in systems at multiple disciplines and more complex products versus often single discipline or simple products. We look outside the system boundaries more often, and it's holistic concurrent engineering, so designing lots of different components of the system at the same time because you have that top-level understanding to be able to do so. It's requirements-driven as opposed to specifications, and it predicts and manages that emergent and emergent behaviour to make sure that the system can continue to function in the event of any faults or unusual behaviours or changes in the environment. So what's emergence? We've talked a little in previous lectures about emergence, but we'll go into more detail here. So it's the system behaviours resulting from the interactions between the individual components and between the system and its environment. We get the positive emergence. So that's the things that realise the functional value. A plane flies through the emergent behaviour of the wings, the engine, the body, the control systems, that gives us flight. But we can also get negative emergence, and this is very important for safety systems. So here's an example, a building that got called Walkie-Scorchy. It was a tower where put in the external environment, and the way it was facing, the parabolic surface of it was very reflective, and it focused the light from the sun to a very, very hot point that even burnt vehicles and burnt the paint off as they drove past. And it's a good one to look up, and there's some interesting videos of people frying eggs from the light from this building. And they had to change that building once it was in the environment, which was very expensive, to deal with the emergent behaviour that was unpredicted there, but could have been predicted. And we can engineer for this emergence. So the value of a system is realised by that positive emergent behaviour. And we need to explicitly engineer that and manage it with a top-down approach. So that's taking the customer needs and breaking them down into components, into blocks, and looking at the interactions between those blocks. If you engineer those components in isolation, you don't get an optimal system. So larger batteries in electric vehicles can decrease the range by adding the mass. It increases the risks of undesirable negative emergence. So One example here that I used to work on the cameras for mobile phones and the PLLs and clock management in there. If you got the frequencies wrong, it could stop the phone receiving any RF signals and any calls while the camera was turned on. So once that camera was integrated into the system, we discovered those problems, whereas we could have predicted them if we'd known more about the system in the first place. It risks incompatibility between components, so often if you get the interfaces incorrect and you don't define those well up front, that's one of the biggest causes of system failure. Moving on, I want to go briefly into explaining the system's life cycle. So systems follow a life cycle from cradle to grave. We start in a discovery phase, which is where we want to spend a large proportion of our time. That's 18% of our effort should be in that early discovery, exploration, and so the start of the system architecture here. So in discovery, we identify the problems, we gather the information from stakeholders, and we try and make sure that we're building the right system for the market. We then want to explore multiple high-level concepts of that system. For instance, if you are asked to provide a means of transport to get into work and you're not given many requirements, you could provide a bicycle, a motorcycle, a car, you could suggest a bus. All of these concepts can be looked at and they can be used to elicit more requirements from your stakeholders to find out more information about what they need from your system. We move on from that stage once we've gathered the requirements into architecture. So that's splitting the system down into the component blocks, into the design and implementation, and then into the integration of that system, the verification, the validation, and the qualification if it needs to meet any particular standards. So that's where we check that the system actually meets the customer needs. And validation should be, and verification should be an ongoing process throughout the design cycle. The earlier you can verify and validate, the better, because the sooner you learn about a mistake to fix it, the cheaper the cost is to do so. We also, as systems engineers, then have to consider the production of our system. How's it's built? How's it tested? Can we do anything to optimize that system to make those processes easier? And we also need to consider the retirement. So what happens when the system's finished its usable life? Is there an upgrade path? Do we have to continue to support it? How will it be disposed of? Throughout the life cycle, we consider two things, divergent and convergent thinking. So divergent thinking is when we create choices in a design. So that's when we expand the information we have out to generate ideas, to be creative and explore different solutions to that problem. And look at the different trade-offs between them, try and find the optimal solution there. So we want to start at the early problem definition, expand outwards and look at the different perspectives, the different choices, and apply some systems thinking. And we can ask a lot more questions. We can refine the problem by using the information we learn and ask more questions about that system. Convergent thinking, on the other hand, is about making decisions. It's about selecting from those choices and using the information, using models, using other techniques to find the optimal solution from all those possibilities. And that reduces the uncertainty in the design by reducing the number of choices, reducing the number of options, and performing the trade-offs in the analysis. So looking at that as how it applies to the system engineering process, at the start we're using divergent thinking as we go through discovery and exploration. Once we've explored some of the concepts, we'll look at the requirements models and try and understand how we can generate the optimal value. And that's convergent thinking, reducing the number of solutions down by understanding more requirements from your stakeholders and optimizing those to get the most utility out of the system. We then diverge again as we move down in levels, as we start to consider different architectural choices for that system. For instance, do we produce a function in software or do we do it in hardware instead? And then we converge again. So once we've decided on the solutions, once we've carried out the internal trade-offs, we go through the design and implementation, the integration, verification, validation, and qualification, to ultimately the one solution that we have at the end, which should be the right solution to meet the stakeholder needs. During this process, we use a model called the V model. So the V model is, we move down on the left-hand side, decomposing the requirements into lower levels of the system. So from the top-level stakeholder requirements through the system levels down to individual components and subcomponents. In the center, we have the specifications here. So they respond to the requirements. So that's when we define what we're going to build. And that reveals the information for the requirements at the low level. So we can understand when we have a specification for an interface between two components, that one component perhaps has to transmit data and the other component has to receive data, and those requirements can then be imposed on that component for them to then write the specifications as part of their system design. We carry out integration and implementation tests in here as we start to integrate the components. That's checked against the specifications to make sure they do what we think they're going to do. But most importantly, on the right-hand side, we're carrying out the verification and ultimately the validation to make sure that we meet the customer's needs. It's very important as we define the requirements that we consider that the requirements are verifiable and can be validated against those needs. And that means thinking about how we're going to test the requirements and involving the verification, validation, and test teams very early, so that if they, for instance, need to build test hardware or test software, they can plan for that in advance. Taking a holistic view, systems engineering is much more than just the engineers themselves and their skills and abilities, or some of the tools that they use, which companies will often buy a tool, like a requirements management tool, thinking it will solve some of their problems. But it's an overall methodology that takes into account the tools, the methods and processes, and the skills and abilities here. So there's a lot of different methods, from requirement solicitation to functional modeling, trade studies, n-squared analysis, different techniques that systems engineers can learn and use. There's tools like Jammer and Doors for requirements management, Confluence, Jira if you're doing more software development, some of the tools for safety like Medini Analyze. So we can use all these pieces of software to help make the life of a systems engineer easier. And there's a series of skills and abilities, so being a good facilitator, being able to apply systems thinking, leadership, negotiation, systems thinking ability in here, big picture thinking. All of these combine together to form an overall view of systems engineering within an organization. So to summarize, systems engineering is beneficial across all projects. It might be required or mandated as your complexity and robustness increases. It's a top-down approach focused on stakeholder needs, so considering multiple solutions, analyzing trade-offs, looking at the emergence, the system as a whole, decomposing and tracing requirements to deliver robust development and manage change, and it follows that lifecycle process. Early validation is important. It's really critical to get the validation requirements at the same time as you start system requirements, so you can identify changes and errors as soon as possible, and you can use models, prototypes, simulation to get that validation done early. You should also maintain communication with your stakeholders just in case the needs change. It's a process here. It's not a one-way flow. There's iteration in there, and there has to be communication. And good systems engineering requires skilled people, processes, methodologies, and the right tools across the organization. Of course, if you have any questions or want to get in touch, my email address is here, and I'd be happy to hear from you. Thank you.